Okay, so we need to write out our formulas for this section. And the formulas that we want, the first one we're going to start off with is that the probability of A naught is equal to 1 minus the probability of A. So this is the complement rule. Basically, if you're looking at not A, then that's saying what's the probability of not having blue eyes? Well, it's 1 minus the probability of having blue eyes. So the have and the not have is always going to add up to 1. There are a lot of different symbols that you can use for this. This symbol is probably the most common that I will use in the class, that I'm most familiar with. But you could use A with a little C up top. You could use the little wiggle with the A, the tilde. You could use the bar on top of A. We don't use computer science exclamation point, not A, so we don't use that. There is another symbol like that means not. We don't see that very often. So you might see different versions of it. I'm probably going to use this one, and it means the complement. So sometimes it's a lot easier when you're trying to find the not of something to use that as opposed to trying to add up all the other probabilities. So we'll look at a couple examples like that. Also, our other formula is the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And when we have questions like this, the or questions, this piece right here, we always want to think about that piece, because that piece is saying to ourselves, mutually exclusive. And we kind of have to think about, is there an intersection to account for? So an example of a problem related to that would be something like the colors of M&Ms. So M&Ms, 20% are brown and 23% are orange and 14% are blue, so on, so on, so on. And if I asked you what is the probability of getting an M&M that is brown or orange, when we look at it, well, there's 20% brown, 23% orange, so I'm going to add those two together. Then you have to ask yourself, are brown and orange, being brown and orange, mutually exclusive? Meaning, can they overlap? Can they happen at the same time? Can I have an M&M that is both brown and orange at the same time? No. So what am I subtracting? 0 out of this situation. So sometimes this is 0, but I can't let you always think it's 0. You have to think about the mutually exclusive component of it, or else, you're going to miss it when it's important. For instance, blizzards. 20% of the people out there like cookie dough blizzards, and 30% of the people out there like Oreo blizzards, and 5% of the people out there like cookie dough Oreo blizzards, because you can have both at the same time. And so if I want to know what's the probability that somebody has a cookie dough or an Oreo blizzard, don't forget that you have to subtract this out because you've counted them twice. Another piece that we have to remember is that the probability of A is not A only. Okay, that's a really important thing. It's any way you see A. If you have a dog and a cat at home, and I ask you, hey, do you have a dog? Are you going to say, no, I have a dog and a cat? No, you're not going to say that. So probability of dog is anybody who has a dog in any way, shape, or form. Probability of a cat is anybody who has a cat. Yeah, I've got a cat. And then this is the people who have both, and they've been counted in both classifications. Yes?
Would the equation be the same if you did probability of only A plus probability of only B plus probability of intersection?
You would, but we just don't see it represented that way. So when we say A, we mean anybody who has A, not only A. And it's an important question, and it's important to think about, because that's not the way we talk about things, but it's the way that mathematics represents those items, okay? And the visual picture that you want to do with this type of problem is this idea of the Venn diagram, being able to look and see if you have those overlapping components or if those circles are separate. So this shows a joint probability, meaning that they overlap. If it's disjoint or mutually exclusive, your circles do not overlap. Okay, so disjoint and mutually exclusive mean the same thing in terms of the probabilities. The two events cannot occur at the same time. So two events cannot occur at the same time. Okay, are we okay with that kind of formula? Let's look at our second formula or third, I guess, that I really want to investigate is probability of A and B. And that equals the probability of A times the probability of B given that A happened. So this piece of that formula says, oh, I got to check independent, question mark. So this is the grandma's candy situation. And this probability of B given A, if A doesn't matter, it didn't change anything, A happening didn't change the probability of B happening, then you get to just straight multiply A times B. But you have to be careful, because that multiplication rule, that idea of, oh, if I want an and, I just multiply those values together, that's not always the case if they're not independent. And with these examples that we're looking at today, most of them are independent, most of them are mutually exclusive. When we look at the next unit, then we're going to heavily get into these more complex scenarios. Please remember that these two are not opposites of each other. The and the or, they're different scenarios. You actually have to set up a different situation in order to ask an or question than when you ask your and questions. Okay, so we have different scenarios. Questions so far? Okay, let's flip to the front. Let's look at the questions. We're going to talk a little bit about the law of large numbers with our first question. And the law of large numbers is basically saying to us, you know, the true probability will be revealed through this long run relative frequency of events, that as your trials approach infinity, you're really going to see the true probability of this occurrence. And the reality is you're living in the short run. All you see is the short run in a lot of your events. And so the mind that hasn't been trained in statistics has two ways of thinking. One way is saying, ooh, I saw a streak of behavior that seems unusual to me. And in the long run, you're going to see streaky behavior. It's going to happen. But all you see is the short run, so you think, oh my gosh, I got 5 heads in a row on this coin flip, and it feels like the coin's not weighted properly. But in reality, if you flipped it 1,000 times, 1,000,000 times, infinite times, you would see those streaky runs throughout all of those, and they wouldn't be that uncommon in terms of appearing, but in the end, the true probability ends up being revealed. So one way of thinking is this idea of, oh, there's a streak and it's unusual, and there's some compensating effect that has to happen next. And there isn't. You know, the coin has no memory. The underlying word that we need to throw out in these types of answers are words about independence. You know, if each event is, if each trial that we do is independent, then the previous results should not affect the probability of what's happening next. Okay, so let's just take a look at these. It says, commercial airplanes have an excellent safety record. Nevertheless, there are crashes occasionally with the loss of many lives. In the weeks following a crash, airlines often report a drop in the number of passengers, probably because people are afraid to risk flying. A travel agent suggests that since the law of averages makes it highly unlikely to have 2 plane crashes within a few weeks of each other, flying soon after a crash is the safest time. What do you think? The first thing that we really need to talk about is the fact that if this is what the AP board is presenting to you, if this is what I'm presenting to you, the very first thing you need to say is that the law of averages is not true. Okay, that's your statement that you need to start off with. There is no such thing as the law of averages. Okay, the universe does not compensate for anomalies or streaky behavior. Okay, so there is no such thing There's no such law of averages. The universe does not compensate for anomalies or streaky behavior. Now, there are a lot of people out there who believe that, you know, this idea of this balancing effect of the universe, you know, that's not my gig. That's not what I believe. Like, I'm a statistician, you know, and I don't look into those and read into those behaviors. Each flight has the same probability of crashing because each flight is independent from the previous flight. One flight's crash does not impact the next flight's probability of crashing. And you would want to write something about that too. Yes, can you talk about human behavior in this and you know, people being more nervous about something so they're a little less good at what they're doing, like maybe in playing sports or whatever? Yes, there's the psychology behind a lot of these pieces, but really we're talking about the idea of events being independent, and the occurrence of one event does not affect the probability of it happening again. Bless you. All right. Part B. If the airline industry proudly announced that it has set a new record, would you be reluctant to fly? Are the airlines due to have a crash? Again, this is based upon the law of averages, which is not true. And so in the end, again, your answer is the probability of crashing is independent and therefore not related to the occurrence of a previous crash or not crash. So those are the kinds of things that you want to talk about in a question like this. Let's look at number 20. So it says, although it's hard to be definitive in classifying people as right or left-handed, some studies suggest that about 14% of people are left-handed. Since 0.14 times 0.14 equals 0.0196, the multiplication rule might suggest that there's about 2% chance that a brother and sister are both lefties. What's wrong with this reasoning? So the mathematics is fine. It's the probability of a lefty and a lefty. And so you take the probabilities and you multiply them together. But what is it assuming when you multiply these? Independence. And do you think we have independence of getting that gene, that trait within a family? Probably not. So in this respect, we're not holding on to the idea of independence. So what's wrong with that suggestion? Assuming independence when these events are probably not independent because it's inherited. Trait? I'm assuming. Okay. Are we okay with that? Okay, let's move on. Let's do some actual problems. Okay, I'm using some formulas. The big piece with this section is notation. We have to get our notation right. That's the key to this, and it's something we're going to have to practice. So let's look at the first one. We've got family music. Your family has an iPod filled with music. It is thousands of songs. You figure that roughly 60% of the songs are music you like, 25% is annoying songs from your little sister, and the rest is stuff from the 80s that only your parents think is cool. Okay, so let's kind of get our mind wrapped around what we've got here. So I have the probability of me liking the music is what? 60? Yeah. The probability that your sister likes the music is 25. And then the probability that it's an 80s song, right? So we'll do 80s is what? Oh, how am I going to figure that out? Well, what do we know all of those probabilities have to add up to? They have to add up to 100%. They have to add up to 1. So if I had a 60 and 25, that's 85. So what's left for the 80s music? 15%. Okay, so I kind of got my thoughts organized. Let's calculate some probabilities. So it's the iPod Shuffle, and you're listening to whatever randomness produces. Okay, what we kind of have to think about this before we start. This is implying that it's randomly choosing a song from the 1,000 songs, and then it could possibly play that song again. It doesn't have to go through all 1,000 songs before it plays it again. All right? Are we okay with that? So it's with replacement. So it's going to go back in there. We kind of have to think about that before we get started. It's implied in this story. All right, what's the probability of an 80s song? So probability of 80s equals, we figured that out, 0.15. B, a song picked by one of the kids. So that's probability of me or my sister, right? So that is probability of me plus probability of my sister minus the probability of me and my sister. The AP board, I need you to write this notation and this formula out. What's the probability of me? 60. What's the probability of my sister? 25. And then this is where I ask myself, hey, in this story, were there any songs that both of us liked at the same time? Nope. So in this case, it's mutually exclusive or disjoint, however we want to call it. And so it's 0. So what do I get here? 0.85. Could you have calculated this a different way? Could you have said not 80s songs? Yeah, you could have. I could have said this is the same as the probability of not 80s, which is equal to 1 minus the probability of 80s, which is 1 minus 0.15, which is the same 0.85. With probability, sometimes there's some flexibility with being able to get the answer that you need. All right, part C. Not one of your songs. So not one of my songs means what? 80s. Okay, so 80s or sister. I could do it that way. Or I could just say probability not one of mine equals 1 minus the probability of mine, which is 1 minus 60. So we get 40. All right, questions on that? With this section, if it's free response, you cannot just throw out some numbers. There's got to be notation, so we have to get used to that. It's something you need to practice. Yes?
Could you do, not the probability of me or my sister? Is there any way you could, calculate that?
Yeah, you can do that. That ends up being whatever's left with a scenario. Yes, you can do that.
That's more than 3, then.
That's a neither.
Okay.
That's a neither. So we'll get to that a little later. So the complement of an or is a neither situation. So in this case, the complement of this or would be just the 80s. Okay. All right, so let's look at the next one, more music. Now you listen to 2 songs. Notice the scenario has changed. The previous scenario was about 1 song. So the questions were really about being mutually exclusive and or not questions. Now I'm changing it to looking at 2 songs. Now my scenario is dictating and questions and independence. That's what we have to think about. So if I look at this one, neither will be songs that you like. So you've got 2 songs, and both of them, neither of those 2 songs will be songs I like. Not the neither that you were talking about, because that was looking at 1 song at a time. So what does that mean? It's going to be not mine and not mine. Does that make sense? Okay. So it's the probability of not mine 1 and not mine 2, which is equal to the probability of not mine 1 times the probability of not mine 2 given that not mine 1 just happened. And this notation helps us think independent. So are they independent of each other? What did I tell you about the song? If the song gets played, can it go back into the shuffle? Yes. So after that first one plays, is what I'm choosing from exactly the same as when I started? Yes. So is it independent? Yes. So really, could I just write it like this? Not mine 1 times not mine 2. Can I just straight multiply those probabilities? Absolutely, because we've decided that they're independent. It's this condition that we have to think about beforehand. So what did we decide was not mine? Mine was 60, right? So it's really that. You can look at it in that way. So what, 0.16? 0.4 times 0.4? It's going to give me 0.16. Okay, let's look at B. Can somebody grab their calculator out, because there's going to be a couple. You got yours? Okay, because I'm not going to be able to do a couple of these in my head. All right, both will be annoying songs from your sister. Okay. So the probability of sister 1 and sister 2 is the probability of sister 1 times, again, the song goes right back into the mix, so it's independent. It's fine. They played Wheels on the Bus. Guess what? It could come up again. So I can just go ahead and multiply sister 1 times sister 2. So what is that? What was sister? 0.25? Times 0.25, right? 0.25 squared. So I get 0.0625. Okay. Part C. At least one will be a song of your mom's choice. Okay, we got to take a little break from this, because at least one is we got to wrap our minds around this for a second. So let me turn back to the back of this original page that we had. And I want to talk about Halloween candy. And I do like the peanut butter cups. Big fan. The boys all sorted their candy last night into little baggies, and we came to the conclusion after we did, bar chart, that about 30% of the candies were peanut butter cups. Okay? I really like the peanut butter cups, and so I'm gonna grab out of the candy bag. They're sorted now, but let's pretend it's all together in some crazy houses that just keep all their candy together. Let's say that I reach into the candy bag and I grab 3 candies, and I want to know what's the probability that at least one of them is a peanut butter cup. Okay, now let's stop for a second. Let's have a little bit of suspension of disbelief in the fact I know what a peanut butter cup candy feels like. I am not going to accidentally be grabbing the Starburst. Like, we know that's not happening, but let's just pretend that it's random. Let's also pretend that when I grab those 3 peanut butter cups, I put it back. So then the second one, it's the same probability, right? Because if I take one out, then wouldn't you agree I have fewer peanut butter cups than I started with? If the bag's big enough and there's enough candy in there, taking a few out doesn't actually change the probability that much, but that's something to talk about at a later date. Okay, so we got to kind of have a little bit of suspension of disbelief. I'm just doing this because I want to organize something for you. What are all the ways in which I can get 3 different candies? Well, I can get a peanut butter cup, and then I can get other. Oh, well, that's unfortunate. I can get other peanut butter cup other. I can get other peanut butter cup. So those are all the ways that I can get 1 peanut butter cup, right? I could get 2 peanut butter cups. We're just going to go with it. Oops. I could get 2 peanut butter cups, or I could get all 3 peanut butter cups, right? And I could get all 3 other. So would you agree with me that these are all the possible ways that I could grab peanut butter cups out of the candy? Yes? Yeah. You're a little distracted now, but that's okay. All right, so how many of these ways are at least 1 peanut butter cup? Okay. Can I grab this scenario? The first one's a peanut butter cup and the other 2 are others. Can that scenario happen with one like go at it? Can this scenario happen at the same time as this scenario? No. They can't. They're all different scenarios. So I would believe that they're mutually exclusive in the way in which they can happen. They can't happen at the same time. So when I say I could get this scenario, or I could get this scenario, or I could get this scenario, or this scenario, I have to figure out my probabilities for each of these scenarios and then add them together, right? Because all of these different scenarios should add up to what? 1. These are all the possible combinations, so all their probabilities should add up to 1. That seems like it's going to be a lot of work, right? Finding the probability of this situation and then adding it to this situation and this situation and this situation. What could I do instead? If I want to find the probability of all of this, would you agree that I could just find the probability of me not getting anything I want and then taking 1 minus that? Okay, that's how we do at least 1. Okay, so the probability of at least 1 is equal to 1 minus the probability of none. None of what you're interested in. So what did I say? What was the probability here? 30% peanut butter cup? So really I'm saying I want 3 not peanut butter cups. So not peanut butter cup is 1 minus 0.3, okay? And that's going to happen to me 3 times. And everything besides this situation will then represent getting at least 1. So it's 1 minus that. So at least 1 is a formula that builds in 2 complements into it. When we learn about binomial, we can do this a little quicker with a binomial distribution, but this is an easier way to do it at the beginning. Today, I cannot ask you at least 2. We don't have that skill yet. We got to study a few more things. Okay, so where'd it go? Where's my peanut butter cup? Okay, so what is this? The probability of at least 1. I don't even remember what we're talking about. Mom's choices, right? Is going to equal 1 minus the probability of neither are moms, right? Does that make sense? Neither moms. So that's going to be 1 minus. What's the probability of, oh, mom, sorry, 80s, right? 80s is the mom. So 1 minus 1.15. Now what do I raise that complement to though, this one? 2, because we're having 2 choices. See, it gets really ugly really quick if I'm looking at grabbing 7 pieces of candy from the bag. Then I've got a lot of different ways in which I can get at least 1 peanut butter cup. So this becomes a quick method. Did somebody calculate that yet?
Yeah.
What is it?
0.2775.
0.2775. Sounds good to me. I'll believe it. All right, let's go down to blood type. Got 2 more problems. We can get through it. The American Red Cross says that about 45% of the U.S. population has type O. I've heard mosquitoes like that blood type more than others. Probability of 40% is type A. Type B is 11. And type AB is, they didn't tell us. So it's the rest. So how do I figure it out? Come on. How do I figure it out? Add it up and then subtract it from 1. So what is it? 9.94? 0.04? Sorry. So this adds up to 96 and then it's 0.04. Okay, so here are all our probabilities. Let's answer some questions. So part A, we've got 1 person here. They volunteer to give blood. What's the probability the donor has type AB? Bless you. Type AB, we just did that complement, so it's 0.04. We figured that out. That's fine. Has type A or type B, so the probability of type A or type B, they need you to write this formula, probability of type A times probability of type B minus probability of A and B. So A was 0.4, B was 0.11. Can somebody have type A and type B blood at the same time? No, so then that's minus 0. So we get 0.56, it looks like. Oh, that's 1, 2, and 3. Fine. Okay. Is not type O, so probability of O not is 1 minus the probability of type O, which is 1 minus 0.45, so that's 0.55. Okay. Those are my OR questions. Those are our mutually exclusive questions. Now I'm going to ask a different scenario. Now I've got people giving blood, and we're looking at how many people? 4. 4 potential donors. What we have to assume is that people are coming into this randomly, that a huge family of people isn't coming in and donating blood. They're all related. They might have similar blood types because of that, blah, blah, blah. Okay? So we kind of got we have to have a little bit of this idea of randomness before we begin. Okay, so B is all or type O. So this is the probability of O1 and O2 and O3 and O4. Are they independent from each other? We just kind of said we're going to assume that. So can I go ahead and just straight multiply it? Hey, if I said it wasn't independent, would you have an idea how to change that probability? Like, you can't just change it from 0.45 to 0.44. You would need a fraction. Your probability would have to be represented in counts in order for you to manipulate that second probability. So when you're given probabilities in decimals, the chances are they're probably going to be independent in situations like this, because you wouldn't know how to manage it unless you had a total number of people. All right, so this is the probability of O1 times O2 times O3 times O4, which is what? 0.45 to the fourth. Anybody got that for me? 0.04?
1. Yeah, 0.041.
Is that what you got? Okay. All right, sounds good. Okay, thanks. All right, 2. No one is type AB. So what do I need to do for that? Well, I'm multiplying 4 probabilities, and what do each of those probabilities need to be? Not AB, right? I don't care what they are, they just can't be AB. So this is the probability of AB not 1 and AB not 2 and AB not 3 and AB not 4, which is probability of AB not times probability of AB not 2, etc. And so that's 1 minus AB, which was 0.04. That's raised to the fourth. So what do we get with that? So it's 0.849. Okay, so 0.96 raised to the fourth, correct? Okay. Okay. What's my third one? I'm running out of room. They are not all type A. Ooh, they're not all type A. Could some of them be type A? Yeah. Could at least one of them be type A? So is this saying basically it's the complement of all of them being type A? Yeah? Okay, so it's a little different than the other problem. So I'm going to say, I'm just going to get through this kind of quickly. I'm going to do 1 minus all of them being type A. So not all of them are type A. 1 minus all of them being type A is, where's A? 40 raised to the fourth. So you're going to take 0.4 raised to the fourth, then you're going to do 1 minus. So what do you get for that? Point oh what? 0.9744. Okay. That seems to make sense. Like, it should be a high probability because it's a lot of different ways that that can happen. All right, let's look at the fourth one. At least one person is type B. Why don't you take a second and try to do it on your own real quick? Try to do this one on your own. At least one. And then don't look up here, but I'll do it up here. All right, what do we got? 1 minus the complement 1 minus 11.11 raised to the fourth. So what's that value? 26? 3726? Okay. Okay. All right, looks good. Let's take a look at the last. This is really important. Talking very quickly just about the idea of independence and mutual exclusivity. So if you examine one person, are the events that the person is type A and that the person is type B disjoint, independent, or neither? Well, can one person be both type A and type B? No, so they're disjoint. Okay, meaning they're mutually exclusive. They can't happen at the same time, which means that it cannot be independent. We're going to talk quite a bit more about that in the next one. If you examine two people, are the events that the first is type A and the second is type B disjoint, independent, or neither? Well, when I'm looking at two people at a time, that's really more of the independent selection. Does one person's blood type affect another, assuming they're random? No. So they are independent. Can they happen at the same time? Can this person be type A and that person be type B? Yes, that those two events could occur. So we're going to talk about this idea of independence, disjoint, and neither the next time we meet. They're really big concepts, conceptual. Okay. All right. That's that. Thanks.